All right, so Lewis structures. This video is going to be just again a review on Lewis structures. We're going to talk about isomers as well as resonance, which they're all related. Okay, so when it comes to Lewis structures, hopefully you got plenty of practice in general chemistry and you got this down because it is really important in organic chemistry, drawing those structures and also knowing the geometry of these things. So first we want to draw only the valence electrons, and we are going to give every second row element no more than 8, and so the goal is to give them 8 electrons so they can satisfy the octet rule. In organic chemistry, we might see some deviations from that beyond the typical exceptions to the octet rule, but we'll see those when they come. And then the next thing is give hydrogen 2 electrons, because hydrogen doesn't want 8, it wants 2, which is like a duet, okay? So best way to practice, or the best way to learn Lewis structures is to just practice them. And so what we're going to do is we're going to go over how to draw this one. This is actually chloroform, makes it go night-night, and CH3Cl. And that is basically what you want to do is tally up the number of valence electrons that each of these atoms brings in. So chlorine brings in 7, carbon 4, hydrogen 3, and so we sum that up and it gives us 14 valence electrons. Okay, now we know that we're basically doing accounting right now. We're doing inventory to see how many valence electrons we can use to make our bonds in chloroform. And so what you want to do is put the central atom is the least electronegative atom. That's not hydrogen. Hydrogen can only form one bond, and so it's not the central atom ever. So that's carbon in this case, and what you want to do next is make a bond to each of the rest of the atoms, and that's what we've done here. Each bond consists of 2 electrons, right? And so we took away 8. That leaves us 6 valence electrons to work with. Now we want to add the valence electrons that we have left to the outer atoms to make sure they all have an octet. And so since hydrogen has a duet, and that's all at once, it's happy. Chlorine doesn't have an octet because it only has those 2 electrons between the carbon and chlorine. And so we add 6 more electrons around it in the form of lone pairs. And now it's got 8 valence electrons, 8 electrons around it. It's got an octet. And that structure, we used up all of our valence electrons, and now, what we would do normally is make sure that carbon, the central atom, has an octet, which it does. And so that structure is done. That's chloroform right there. So the next one, CH4O, I've written the formula this way on purpose because it's going to kind of trick us. So we're tallying up our valence electrons. We got oxygen with 6, carbon with 4. 4 hydrogens brings in 4. That gives us 14 valence electrons. Okay. Now, central atom is carbon again because it is the least electronegative atom besides hydrogen. And so we put carbon at the center, and then we make bonds to the rest of the atoms. But here's the thing. Notice there's 4 hydrogens on there, and we can only have 4 bonds to carbon, and so we don't want to draw that 4th hydrogen on the carbon because we need to make that carbon-oxygen bond. And so the way it's drawn is weird and it's not very suggestive, but we should be able to figure it out and know that oxygen also wants 2 bonds. And so this would actually be more appropriate in the way we draw that molecular formula, CH3OH. And so that oxygen has the last hydrogen on it. So remember, carbon always has 4 bonds unless it's charged. And then oxygen has 2 bonds unless it's charged as well. So drew that there. Now we've used up 1, 2, 3, 4, 5. We made 5 bonds, which is 10 electrons, right? So we used up 10 of the 14, gives us 4 left to place on the outer atoms to make sure they have an octet. Again, only oxygen is present, or only oxygen needs the electrons, and once we've done that, everybody's happy. And so that's the end, that's the final structure. This is actually methanol. All right, so doing a couple other structures. Again, practice makes perfect-ish, because nobody's perfect, even I mess up. CH2O, or you can also draw it as H2CO. It kind of just depends how you want to. You'll see it both ways. So oxygen has 6 valence electrons, carbon has 4, and hydrogen brings in 1, but we've got 2 of them, so that gives us a total of 12 valence electrons to make this particular molecule. Now, carbon is the central atom. We'll draw bonds to each of the rest of the atoms, and that uses up 6. Sorry, not sure if you can hear that, but that was the ice machine down the hall being a jerk. So we used up 6, and that leaves us with 6 valence electrons to make everybody else happy. And so now oxygen's happy when we add those 3 lone pairs, but carbon's sad. We used up all of our valence electrons, so what are we to do? Oh my. Well, remember that we can share electrons, right? So we're going to share this pair right here and to create a double bond, a carbon-oxygen double bond, also known as a pi bond in there too. And that gives us this structure, and now everybody's got an octet, and everybody's happy, and there you go. That's actually formaldehyde that preserves tissue. And so if you take in animal biology, they use that, or probably formalin, which is just a solution of it. But now let's look at molecular oxygen. So we've got 12 valence electrons coming in total. We've got no central atom because it's only a diatomic molecule, and we put all of it. Oops, I did not do my accounting properly. I didn't do inventory. So we originally made a bond between oxygen and oxygen, and so we used up 2 electrons from that 12. So let's go ahead and do the math. We got 10 valence electrons to put as lone pairs around the oxygen atoms. So that's 6 right there, 8 and 10. So now the oxygen on the left's happy, but the one on the right doesn't have an octet. He's angry. So what we can do again, just like in formaldehyde above, we can share. So we're going to share a lone pair to create a double bond between the 2 oxygens, and that gives us this as our final structure. And oxygen's happy, kind of. Let's do a couple more so that we're awesome at them. And let's do HCN. So this is hydrogen cyanide. This is cyanide gas. This is also what makes you go night-night, but permanently. We've tallied up our valence electrons. We got 10 valence electrons, okay? Carbon's the central atom, and we used up 4 valence electrons to make those 2 bonds, right? Now we want to place the rest of the 6 on the outer atom to give it an octet, right? But carbon's not happy. He's only got 4 electrons around him. So what we want to do is kind of think ahead, right? And use these 4 electrons right here, the 2 lone pairs, to make 2 more bonds. So what we've actually made is a triple bond, and now carbon, nitrogen, and hydrogen are all happy, and that's the structure of cyanide gas. All right, so elemental nitrogen is N2, comes in with each nitrogen has 5, so we've got 10 valence electrons to work with. Make a bond between each of the nitrogens. That gives us 8 electrons to place on the outer guys. Now, thinking ahead as well, in order to make nitrogen have 8 around it on the left, we got to use 2 lone pairs, and that's going to make a triple bond. So notice elemental oxygen had 2 bonds, but elemental nitrogen had 3 bonds. And this is actually consistent with the rules, right? So we said oxygen's in row 6, and 8 minus 6 is 2 bonds. Nitrogen is in group 5, and it has 8 minus 5 is 3, so it has 3 bonds. So it's all making sense now, right? Hopefully. This is like memory, this is recall right now. So remember that thing called formal charge? Well, let's talk about that for a minute. So formal charges are really important in organic chemistry, just because formal charges as well as even like partial charges are going to dictate where the chemistry happens oftentimes. And so when we start doing synthesis, it's going to be really important. So when an atom has too little or too many electrons, a charge is present, okay? And so that's going to be the formal charge. And what we mean by too little, that would give us a positive charge, and then too many electrons, that would give us a negative charge. Think of it. Electrons are negative, right? If we have too many negative things, it's going to give us a negative charge. If we don't have enough of them to balance things out with the protons in the nucleus of that atom, then it's going to be positive. So formal charge Fc is equal to, there's a formula for you, number of valence electrons minus the number of electrons an atom has, or it owns, quote unquote owns. Or we can simplify this, in my opinion, to the number of valence electrons minus the number of LPs, lone pairs, minus half the number of bonding electrons. And so the lone pairs and bonding electrons, that unit right there corresponds to like basically the number of atoms and number of electrons in atom ohms. So this is the same formula, it's just breaking it down a little bit more. And so what does this mean? What are we doing here, right? So let's just try a problem. So O3, does anybody know what that is? Any takers? Think about it. What is that compound called? It's called ozone. Remember, it used to be like a thing, the ozone layer. It's actually a cool podcast about that on stereochemistry. It's called Stereochemistry, which is an amazing name, by the way. You'll find out why later. But they talk about the ozone layer and how they figured out it was being depleted, and then why they won the Nobel Prize. Anyway, this is the structure of ozone right here. We've got 18 electrons, all taken care of by coming in with the 3 oxygens, and then the structure checks out because all the octets are fulfilled. However, if we look more closely, we can see that there are charges. Okay, so what we want to do is getting text messages. What we want to do is apply to that formula. So the oxygen here in red, or the one that I boxed in red, the number of valence electrons is always going to be the same in this molecule because they're all oxygens. So they all technically come in with 6 valence electrons. That's what an inherent property, if you will, feature rather. So 6 valence electrons minus the number of lone pairs that it has. So let's highlight those 2 lone pairs. And so rather than put 2 lone pairs, we're going to put 4 lone pair electrons. Okay, because that's really what we're focusing on. And we're going to subtract half the number of bonding electrons. And so we've got 2 bonds to that adjacent oxygen, and that's a total of 4 electrons, right? And so we're going to subtract half the number of 4 bonding electrons, which is 2, right? So once we do the math, we can see that we get 6 minus 4, which is 2, minus 2, which is 0. All right, and so that's why the one in red has no formal charge, because it adds up to 0. Let's check out this blue one. 6 valence electrons, and now when we're looking at the lone pair electrons, we've got 2, and then half the number of bonding electrons. A quick way to do this is just circle the electron that's bound to that oxygen, or like the way it's drawn. It's directly touching that oxygen, and then that's 3 of them, right? And so I just jump to the quick 3 that way rather than doing half of 6. And then we get positive 1. So that oxygen right there has a +1 formal charge. And that's because it actually has, it's lacking one of the electrons that it had when it was, so it has 5 electrons around it, and it usually wants to come in with 6, right? So lacking 1 has +1 charge. Looking at the one in black, we've got 6 minus 6 lone pair electrons minus the 1 that it's got in the bonding, and that gives it a -1 charge. Formal charge is -1. And that's because it has, beyond 6 valence electrons that it comes in with, it has an extra one around it. And so it has an extra negative thing around it, and therefore it's got a negative charge. Okay. Hopefully it makes sense what I mean by like just jumping to the number of bonding electrons, half the number of bonding electrons. You just kind of circle the dot that's kind of directly adjacent to that atom, and I like to do it that way. And then if you've got one less, or one or if you have less electrons than the valence electrons that it comes in with, then it's positive. If you have too many, then it's negative. All right, so this is acetate. Remember that from general chemistry. Uh, we're not going to really focus on the CH3 or the carbon in the carbonyl group, which I just redrew for you, sorry, because the oxygens are the ones that are probably going to be the charged ones in this case. So the oxygen right here in red, 6 valence electrons minus 4 total lone pair electrons. And then we've got 2 dots right there representing 2 bonding electrons. And then that adds up to 0, or it subtracts up to 0. All right, the one in blue, right? So we've got 6 valence electrons again for that. And then we want to subtract the 6 lone pair electrons. And how many of the bonding electrons did we count? 1 of them. And again, that's an electron beyond the 6 that it came in with, so it's got a -1 formal charge. And so that's where that overall charge comes from in the upper right that I wrote. Okay, you can draw it like this also. It's typical for organic chemistry. We have that negative charge with the circle around it. And there you go. Okay, so just more or less to kind of tally something up for you. Carbon has 4 bonds. We've got nitrogen with 3 bonds and oxygen with 2 bonds. So what happens if we deviate from that, right? So what we can do is kind of classify this as what's normal and say like this is what would they have when they are neutral. Okay, but what if they're charged? What if they have a formal charge? So carbon with 3 bonds here, and then carbon with 3 bonds here, but with a lone pair. Okay, how are they going to differ? Nitrogen with 4 bonds, and then nitrogen with 2 bonds, but 2 lone pairs. So notice we're kind of deviating from the standard number of bonds that they typically have. So oxygen, if it has 3 bonds rather than 2, we can have 2 different structures for that. Or if it has 1 bond with 3 lone pairs. So that's a lot, right? What's going to happen? So this is more or less just to summarize for you kind of what the charges are looking like. Again, the way I like to think about it is carbon has 4 valence electrons. I've highlighted in blue. There's 3 surrounding it, right? So you can think of it like this. 4 minus 3 is 1. And that's why carbon's got a positive charge. Nitrogen typically has 5 valence electrons, and it's only got 4 blue ones around it, and so 5 minus 4 is 1, positive 1. Same for the oxygen. 6 minus 5 is positive 1. And so if we take a look at the structures on the right, we've got 5 electrons around that carbon, and that's 1 more than it typically has, which is 4 when it comes in with. And so since it's got an extra negative thing, it's got that negative charge. And so the same thing can be said for the nitrogen as well as the oxygen. There's 6 electrons around the nitrogen, and there's 7 around that oxygen. And so that's why they each have a negative charge. Okay? Now, let's move on to isomers. So isomers are, there are a variety of different isomers that we will discuss in this class. And so there are things such as constitutional isomers where there's different bond connectivity, and then there's stereoisomers where they have different three-dimensional orientation. In any case, isomers are different molecules, but they have the same molecular formula. Okay, so like the same number of carbons and hydrogens and oxygens. Those are, if they're different molecules but the same formula, then they're isomers. and they both have octets. Okay, so if we're comparing two isomers, they'll have octets fulfilled in all of them. For example, we've got ethanol here, and it's got, or I guess I'll draw the other molecule for you real quick. We've got this guy right here with an oxygen is at the center now. It's not at the end, with its two carbons on the either side of it. And this is called dimethyl ether, something we'll become familiar with, or at least the functional group and the names and stuff. Both of these have a chemical formula of C2H6O, except one is for usually like popping bottles, right, on the left. Ethanol is found in alcohol that people drink when they drink responsibly, because that's the only way to drink. And then the ether on the right side, I had to put this in here because ether was typically used for anesthetic. It makes you go kind of night-night, you don't feel it, and so they could operate on you back in the day when they didn't have the normal anesthesia. Curious George was huffing ether. This is an actual book for children, and I have it at home. I was reading to my son, and I was like, whoa. He also smokes a pipe in that children's book, which, yeah, we've come a long way when it comes to children's books. Now, they're a little different. I kind of like that OG Curious George book, though. It's really funny. So, exceptions to the octet rule. Somebody once told me, like, why are there always exceptions to everything? There seems to be more exceptions than there are, like, definitive rules. Not necessarily true, but a valid thought. So, hydrogen, for example, it forms a duet, right? That's not 8. Beryllium, it's only got 4 around it. It does not have an octet at all, not even close. Boron and aluminum, these guys, remember, according to the rule, they have 3 bonds each. And so these guys are electron deficient. They have only 3 bonds. Now, there are cases where you can have more than 3 bonds, more than an octet as well. And that would be something like sulfur. H2SO4 is something super common we've already come into contact with, sulfuric acid, and you can see it's got 2, 4, 6, 8, 10, 12 electrons around it. That's way beyond the 8 for the octet. Phosphorus, H3PO4, that's got 2, 4, 6, 8, 10 electrons around it. So again, that's something called an expanded octet. And it's more than the typical octet because sulfur and phosphorus are in row 3, which has, remember we had the sp orbitals for row 2, or snp orbitals for row 2, and then for row 3 we have the sp orbitals as well as the d orbitals. And so these d orbitals are what allow sulfur and phosphorus to have that expanded octet. Whereas boron and aluminum, for example, only have the S and P, and these guys actually have a vacant p orbital sticking up and down because they have a trigonal planar geometry. And so these guys are electron deficient, while the sulfur and phosphorus are electron rich. And so again, electron deficiencies and electron richness is going to help dictate what type of chemistry we're doing in organic chemistry. And so it's really helpful to understand these types of things and make sure that you're solid with this. This is your foundation. So resonance. What is resonance, right? It's the same placement of atoms, but a different arrangement of electrons. So what does this even mean? I know resonance is kind of tricky for a lot of people in general chemistry, so let's check it out. We've got this molecule right here. This is an amide, and we've got a negative charge on the nitrogen, right? So this arrow right here, it's like a double-sided arrow, not the equilibrium arrow, but one line with 2 kind of arrows on it. That is the resonance arrow. So that's what you use when you're drawing resonance structures, and not to be confused with the equilibrium arrow again. Okay, and so the same placement of atoms. You can see the general structure as on the left and the right is the same, but it's got a different arrangement of electrons. So there's a bond in a different place, and there's lone pairs in a different place. So that's what we mean by resonance. And so I've drawn in red where the lone pair is going in between the carbon and nitrogen to form a red bond on the right. And then the red bond between the carbon and oxygen in the left structure goes up to the oxygen in the form of a lone pair, because it's 2 electrons in every bond, and both of them leave that carbon, so that way it can still have an octet and not have more than 4 bonds on the structure on the right. Okay, and so this is hopefully helping us follow the electrons by highlighting them in red, seeing where they go. So this molecule on the bottom, we've got that resonance arrow again. And we got the positive charge on the oxygen on the left, but now it's on the right. I'm sorry, now it's on the carbon on the right. And to follow the electrons again, I'll highlight one of the bonds in red, and we'll move both of those electrons in that bond to the oxygen, and then we will show that where basically in the form of a lone pair in the structure on the right. So notice in both of these resonance structures, the charge remains. That charge was maintained in both structures, and specifically like the net charge is what we want to look at. So the net charge on the top molecule is -1, on the bottom is +1. And we're good to go. Okay, so what we want to do here is compare isomers and resonance structures, because we might get the two kind of mixed up, and so it's important to differentiate between the two. So looking at the left structure compared to the right structure, what we want to do is basically look to see, remember isomers are same molecular formula, different arrangement of atoms, or different bond connectivity. Resonance is just same bond connectivity but different arrangement of electrons. And so if we look at the upper one, we can see that it's an isomer because the carbon on the far left, that one with the double bond carbon, that's got 2 hydrogens on it, when the one on the right has 3. And so that's different bond connectivity, so it has to be isomer. While the one on the bottom is going to be a resonance structure because it's got a different arrangement of the electrons only. So carbon at the center and then oxygen's kind of around it, right? And we can see in red how that resonance structure would kind of play out. So there you have it. Bam! Let's do how to draw proper resonance structures. Why not? Want to do well, right? So the first rule, obviously the atom arrangement needs to be the same, right? And so that's kind of one of the rules we kind of established before, where the resonance, how we can distinguish resonance between isomers. So the arrangement must remain the same. And then here's an example for you. And we've seen this before, so let's just zoom through this. Boom, boom, boom. Draw the lone pair creating that carbon-nitrogen double bond, and then breaking the carbon-oxygen pi bond. Kick that up to the oxygen. Got a negative charge, charge remains, right? So now the second rule for how to draw proper resonance structures is the structures must have the same number of unpaired electrons. And so this is different than non-bonding electrons, right? So those lone pairs are always, they're pairs, right? And so if we're talking unpaired electrons, then we mean like lone electrons. And so sometimes eventually we'll see that we can have radicals, which is where we have an electron by itself. And so formaldehyde, if we were to split that up into that bond that has 2 electrons, if we split it up into just 2 single ones, we can have those on the structure on the right drawn in red. Single one goes to oxygen, single one goes to carbon, and that's not okay because it's not the same number of unpaired electrons. Okay, That one's kind of silly, but it's important. And it'll be more important later. So another thing is we must uh, have valid Lewis structures. And so typically, this is going to be we're going by the octet rule, right? So it's important just to know what's a valid Lewis structure. More specifically, we have this particular carboxylate or formylate ion, and if we were to, oh, sorry, I forgot to cross that out. That means we can't do the resonance structure, right? Because there's the unpaired electrons are different on either side. We can't do this one either because if we did place the lone pair to create another carbon-oxygen double bond, we would have way too many bonds for carbon, right? We would have 5 bonds to carbon, and that gives it a negative charge, obviously, but carbon can't handle that many electrons. It does not have the ability to have an expanded octet. It's not in row 3, and it doesn't have d orbitals. So 5 bonds, get that out of here. Don't ever do that. That's just silly. You can do 4. You can maybe even do 3 sometimes, and we'll see that later. But don't ever do 5. It's wrong. All right. So, but notice, well, actually, let's just move on. So, notice, well, the curved arrow notation that I was doing just to kind of show you the flow of electrons. So, you typically, the curved arrow notation is actually for the electrons only. So electrons are what's doing the moving around and the attacking, and so you don't ever want to have an arrow go from a positive charge to a negative charge because it's always going to be the negative thing going to something else, right? So curved arrow notation is just allowing us to shuffle pi electrons, and we always start with the electrons and move somewhere else. And wherever the end of that arrow is, the point of it, that's where they end up. And so we can start with a lone pair to make a pi bond. Okay, and so it starts with the lone pair, but then it ends at the atom, or it could end at a bond, right? And so that's what would be making that pi bond. So if it ends at the atom, then it's just a lone pair. So here's an example for you. We've got, oh, you know what? Sorry. I want to put a little caret right there. So start with a lone pair or a pi bond, and then you can make a pi bond, or if you end in an atom, you can make the lone pairs, okay? And so, for example, benzene, this guy right here, if we shuffle those pi bonds around, we can get a different resonance structure of benzene with a different arrangement of the electrons, okay? So both of these are acceptable and equal. So here's another example. We've got carbon-carbon double bond, and then we've got a carbon-carbon single bond, but we got a positive charge on that last carbon. So now what we're looking at is shuffling the pi bond to form another bond again. But now, once we draw that new structure on the far right side, remember that that resonance arrow is important. And then we have a carbon-carbon double bond on the right side, but this guy right here, he's only got 3 bonds, and so we got a positive charge there. So basically what we did was we shuffled the pi bond, but then we also have to move that charge. So charge needs to be maintained the whole time, remember? And so again, those are valid Lewis structures for that particular compound as well. Now looking at this guy, it's going to have a slightly different setup. Now we've got this particular carbon here with a lone pair that can create a carbon-carbon double bond, and then that would be too many bonds to that carbon, so we had to lose a carbon-oxygen bond, and that goes up to the oxygen as a lone pair. And now we've got the structure on the right. And so I'm drawing these in red now for you so that we can clarify where things are going and basically how we're maintaining throughout. Okay, so this is a 3-atom system, and this is very typical for resonance structures, and we should, especially with this CO double bond, those are like super common for resonance structures, and so become familiar with that and be comfortable with it. So when you're doing these though, what you want to do is look for pi bonds that are next next to vacant p orbitals. Or what you can do is look for p orbitals that are occupied by 1 or 2 electrons. So I'll give you a couple examples just to see what we mean by this. So the first thing I want to draw is something called a tropylium ion, where we've got a positive charge on that top carbon. We got an adjacent pi bond, right? And so that positive charge, we need to know that there's vacant p orbital, just like there was in boron and aluminum. And that pi bond can, or that pi electrons can kind of go in there. And then what that does is it shuffles the positive charge around the ring. You can do it again and again and again. And so we'll draw another structure. Notice the positive charge is going where the pi electrons came from, right? And so we can do this all day. And this is important for it's important to know just because resonance provides some level of stabilization. That positive charge is a really reactive compound, and resonance stabilization is a thing that we'll touch up on more a little bit later. Okay. So now looking at the next portion of that rule. So there was vacant p orbital that the pi electrons can do resonance with, or occupy to do a resonance structure. But then there was also when we have 1 electron adjacent to that pi bond, right? So that pi bond is adjacent to a carbon with only 1 electron. This is a radical. And we can draw a resonance structure as such. I'm not going to draw the arrows on this one because they're a little bit different, and we'll see them later in the semester because they're structured differently. But now let's take a look at this structure here. So the last one was when we have a resonance structure, or we want to look out for a pi bond adjacent to a p orbital that is occupied by 2 electrons as well. And so in this case, this is a pi bond adjacent to an oxygen that has pi electrons, or p electrons. And so we can form that resonance structure as well. And so these are just a few examples of how we can do that, or how we can apply that rule for drawing resonance structures. And so again, just to summarize, top one is vacant p orbital, middle one occupied by 1, and then the bottom one is occupied by 2. Okay, so another kind of vocabulary word associated with resonance structures, which you should have learned in general chemistry, is hybrid. And a hybrid resonance structure is basically the average of all the resonance structures possible. So like that tropylium ion above, I drew a bunch of resonance structures, right? And so there's a hybrid structure that we could draw that would kind of sum up what it looks like. So benzene is another example. We can draw multiple resonance structures of this guy where the double bonds are in different locations. And so these are both equal resonance structures, no priorities on one or the other, what the molecule prefers to be like. And the hybrid is going to look something like this, where the double bonds are not solid anymore, but they're dotted lines. And so oftentimes you might see me abbreviate a benzene ring like this as well. So this is kind of depicting the same thing, where we have the alternating double bonds within that structure. Okay, so just keep that in mind if I draw it. Okay, so another example of a hybrid would be, let's draw another structure for you. All right, so this guy is acetaldehyde, and we've got one structure on the left. We can draw another structure on the right. We basically split up the pi bonds to give an oxygen a negative charge and a carbon a positive charge. So we can classify these in a different manner. So major contributor on the left, minor contributor on the right in terms of resonance. The one on the left is the major because it has more bonds and fewer charges, while the one on the right has obviously less bonds and it's got those charges. So we don't want to have charges if we don't have to. And so the hybrid in this case is going to look like the major contributor. And that's going to be the case always. And so this is important because that's how it's probably going to react as well. If you have different structures, but one is a major contributor, that might dictate the way the molecule reacts. And so it's important to know this as well. So let's take a look at this guy. We've got two different structures here. We've seen this resonance before, right? So now what does a hybrid look like? Well, we've got that dotted line where the double bonds are forming, right? And so one thing we also want to note is we can instead of the negative charge being just -1 on the nitrogen or -1 on the oxygen, it's delta negative on the nitrogen and the oxygen. So partial charges on each. And so the dotted line, double bond goes where the single bond becomes the double bond. And the delta positive, which we don't have in this case, or the delta negative, which we do, go where the charges are in each individual resonance structures. Okay, and so there's more to come on this for sure. So let me know if you have any questions. Bye. Oh, I forgot. I gotta leave you with a little joke here. Let's see. What do we want? What do we want? What do we want? We want something good, right? Oh, did you hear about the zombie dogs? They were terrorizing the neighborhood. Ha. Anyway. All right. Bye.